Hello, my name is Eitan, and I'm a member of the Industrial IoT Support Team, which is part of the IIoT Development Group in MIL. This webinar deals with the Motorola MOTOTRBO Industrial IoT SCADA and M2M solution. The objectives of this webinar are to understand what is an industrial IoT solution and how can a Motorola MOTOTRBO system be utilized for an industrial IoT solution. First, let us clarify the terminology used when dealing with industrial IoT, aka SCADA and M2M. SCADA, which stands for Supervisory Control and Data Acquisition, refers to a real-time process control system used to centrally monitor and control remote or local equipment such as motors, valves, pumps, relays, sensors, etc. SCADA is a combination of telemetry and data acquisition. M2M, which stands for machine-to-machine, refers to Intelligent Electronic Device, aka IED, an acronym. It's used for data connectivity and communication to expand the user operational view and control. IoT, which stands for Internet of Things, refers to a network of physical objects that features an IP address for data connectivity and communication across a network of networks. The term network of networks stands for a combination of communication networks capable of working together to collect and communicate data across the operations. So industrial IoT stands for connecting operational and information technology across industrial and critical infrastructure environment to leverage data for the process automation and monitoring necessary to increase productivity. The figure in front of us displays the key entities in Motorola IIoT solution. Our SCADA RTU serves as an IoT gateway to various IoT sensors and operational technologies. The collected data is transported over LMR or other communication network to an HMI via the FEP, which stands for Front-End Processor Gateway. The FEP provides a two-way path to the communication system between the RTU and the IIoT manager host entities. The HMI could be a manned control center or a mobile application devices such as a smartphone or tablets, etc. The multiple IIoT RTUs, gateways, and FEPs in the system may communicate over a highly sophisticated hybrid data communication network by utilizing a variety of radios and or communication links. Radio links may include conventional analog trunk, digital trunk, and both analog and digital microwave radio technologies. Line links may include point-to-point, multi-drop, cellular packet data modems, and local area networks. The IIoT RTU may communicate with other RTUs with one or more computerized control center that are connected to the communication network and with third-party PLCs and other devices. Each RTU can communicate with the control center via other RTUs that serves as store and forward or network communication node in the overall network, hence extending the communication coverage and lower its costs. The IIoT RTU communicates upward with the control center and downward with the third-party intelligent device and PLCs using a variety of standard protocols such as Modbus, DNP3, and other specialized drivers. Motorola offers several RTUs and FEP models types in the company IoT portfolio. The ACE3600 RTU combines the local processing of a PLC with the superior communication of a remote terminal unit for an all-in-all high-performance unit. It allows seamless integration and multiple PLCs, RTUs, and intelligent electronic devices. It has a powerful processor combined with versatile input-output modules, allowing this RTU to be used for the most demanding IoT applications such as electric utilities, oils and gas, water and wastewater, siren and PA, and many more. The ACE1000 RTU facilitates high reliability and interoperability at a lower cost. Its powerful processor combined with the flash and RAM memory allows this RTU to be used in the most demanding IIoT environments. The ACE1100 FEP is used at the central site to provide a two-way path to the communication system and to remote ACE1000 RTUs from the IoT manager entity. This FEP supports a standard IoT protocol to communicate with the IoT manager and interface with the RTUs via MDLC. It also provides the ability to mirror all the information from the remote ACE1000 RTUs to the IoT central control center, so no direct interrogation from the control center to the remote site is required. The ACE IP gateway, also known as ACE4600, is an IoT gateway from the ACE1000 or ACE3600 RTUs to an IIoT control center. It acts as an interface between the MDLC world and the TCP IP world. Motorola offers an M2M system in the company IIoT portfolio. The IRM 1500 system supports a multitude of data applications over the Astro P25 integral voice and data radio system. It befits the needs of personal and public works, electric utilities, and petrochemical markets to know exactly what is happening in their distribution system at all times. The IRM 1500 modem transports incoming data from RS-232 or RS-485 over the air while utilizing the P25 data channel to the IRM 1500 server, which resides in the Customer Enterprise Network, or CEN, and is connected to the IIoT Manager entity. Now that we have established some background as to what the IIoT solution is, I would like to go over how it can be utilized over the MOTOTRBO radio infrastructure. The MDLC is Motorola's proprietary protocol, which incorporates all 7 layers of the OC standard, adapted for IIoT. This protocol is optimal for narrowband communication channels. The Motorola IIoT network utilizes this proprietary MDLC protocol, so both FEP and each RTU has all the 7 layers of the MDLC protocol available for them. The MDLC facilitates the communication among all its sites in the system. The MDLC supports multiple logical channels per RTU physical communication port, enabling simultaneous central to RTU and RTU to RTU sessions. It also enables each RTU to simultaneously run several kinds of communication, such as reporting alarms by contention, online monitoring, performing extensive diagnostics checks, etc. The PTP or PMP link standing for the point-to-point and point-to-multipoint links could be two-way radio, leased line, LAN or WAN, or multi-drop wire LAN. Motorola ACE1100, ACE1000, ACE3600, and ACE4600 units could be connected to a MOTOTRBO radio in digital mode to use MDLC over IP or via MOTOTRBO digital mode radio system. Motorola ACE3600 and ACE4600 also support the analog mode of the MOTOTRBO radio, same as it did on the legacy radios, the CDM 750, CM200, etc. In the digital mode, the MOTOTRBO radio is connected to the unit's USB port, and the connection is a USB host running an IP over RNDIS. On this mode, the radio functions as a modem. The unit sends the radio requests, and the radio handles everything. On Connect Plus system, which is also digital mode, the radio port is a non-IP connection, and the port is utilizing a specialized protocol called XMP. The FEP in this scenario is connected to the XRT gateway over an IP port, running an XRT protocol to communicate with the radios. In the analog mode, the MOTOTRBO radio is connected to the unit's GRI piggyback and is supported only on the DMO and single repeater topologies we'll see further on our slides. On this mode, the radio functions as any analog radio and is controlled by the RTU. The RTU utilizes a channel access mechanism to activate the radio. As stated here on the DMO topology, the radios share a single channel. On the single repeater topology, the radio have separate TX and RX channels opposite to the repeaters channels, and the IP site connect is utilizing several repeaters, having them connect through IP, thus extending the range between the radios. The MOTOTRBO Connect Plus topology is a trunk system where the radios communicate over repeaters, which are controlled by the XRC, which is the controller. This system is utilizing multiple channels and could utilize multiple control channels. This is the DMO topology. As you can see, all the units have a radio, and all of them communicate over a single channel. The RTUs burst the information towards the FEP, which is pulled by the control center application. The FEP can pull the RTU exactly the same method as the RTU. This is the single repeater topology, and as you can see, all the units have a radio, and all of them communicate over two channels through a repeater to other units. So here, the RTU bursts the information towards the FEP on the repeater RX channel, and the repeater transmits the data on its TX channel, which is the FEP RX channel. The FEP is pulled by the control center application later. Here, the FEP can also pull the RTU exactly the same method as the RTU, just the other way around. This is the IP site connect topology. And as you can see, all the units have a radio, and all of them communicate over two channels through a repeater to other units. Only the RTUs are connected to repeater 2, while the FEP is connected to repeater 1. So here, the RTU bursts information towards the FEP.
Thank you. Hello, my name is
RX channel. And the repeater transmits the data over IP to repeater 1, which transmits the data over the air on its TX channel, which is the FEP RX channel. And again, the FEP is pulled by the control center application. Here, the FEP again can pull the RTU exactly the same method as the RTU, just the other way around. This is the Connect Plus topology. Here, only the RTUs are connected to a radio, while the FEP is connected to the XRT via the sort of send switch. So here, the RTU bursts information towards the FEP. The RTU will request a channel from the XRC using the control channel. Once authorized, it will switch to the designated channel and transmit the information. The data will reach the XRT, which will route it to the FEP. When the FEP wants to pull data from the RTU, it will send a frame to the XRT, which requests a channel from the XRC. Once channel is assigned, data will be sent over the air on the designated channel. I just wanted to highlight big ideas on this slide. As you can see, what is bolded below would be more detailed information to just speak to as in reference to the bullets on the side. A 3600 RTU may be connected to two radios provided they have different local IP address. The MDLC time synchronization is not recommended due to long delays added by the radio or repeater, and the NTP is not supported either, as it is not an IP-based communication. In single repeater or IP site connect topologies, the unit attached to the MOTOTRBO radio may initiate or receive MDLC group calls over a single link ID. And MDLC data throughput over MOTOTRBO system is between 800 and 900 BPS, which is less if the frequency or slot is shared for voice and data. Connect Plus offers a limited bandwidth data service compared to the MOTOTRBO digital operation. The XCMP protocol RT uses the XCMP device, and radio is the XCMP master, routes the packet data between the RTUs and its Connect Plus option boards. The actual address of RTUs over the air is the subscriber ID of the radio configured in the CPS. It is not possible to communicate directly between the RTUs because the direct communication between radios for raw data is not allowed. With the MDLC communication could be routed between the remote RTUs via the FEP. The MDLC time synchronization should be avoided because of the long delays added by the radio or repeater. NTP is also not supported, and as it is not an IP-based communication. There is no support for MDLC group call on the Connect Plus. Hence, trying to transmit group call will result in it being replicated and being sent for each RTU. There is like a 2.5 seconds for FEP from the LAN and 7.5 seconds per RTU from the radio delays. During this time, all the communication via the physical connection is withheld. So therefore, it is the best practice would be to send to each RTU separately. I would like to summarize what we've learned in this webinar. We've learned what is an industrial IoT solution and how to utilize the Motorola MOTOTRBO system for an industrial IoT solution. Thank you very much for watching this Motorola Industrial IoT over MOTOTRBO radio infrastructure webinar. Thank you very much. Bye-bye.